So we're now kind of ready to start the last talk of this session, and that's Professor Richard Statman, who's going to talk to us about products in a category with only one object. Hello, take it away, Professor. Oh, the vagabond sun is back again.
You're muted right now, Richard.
Group. The Vagabond Group is one of three groups. That was defined by Richard Thompson in the 1970s. It has a very interesting history. I'll tell you a little bit about the history. So the plan for my talk is the following. I'll tell you a bit about the history and how the son of the vagabond, which is a monoid, has been rediscovered.
Richard, would you mind speaking up or bringing the mic closer, if you could?
I'm sorry, can you hear me?
We're having, people are saying in the chat that it's too quiet.
I'm speaking as loud as I can. Okay, so we'll do the best we can. I want to talk a little bit about the history of the monoid I'm going to speak about. It's been rediscovered at least 9 times, and this is just a list that I found. I'm sure that there are other rediscoveries. And tell you why what is contained in the paper is actually applied category theory. That will be something that needs to be talked about. I'll tell you a little bit about the results themselves. Okay, so the first example comes up in 1961. Janssen-Tarski wrote down basically the theory of a surjective pairing function. First order theory, as an example of something in universal algebra. And I read the paper years and years ago, and to be honest, I don't remember what this was supposed to be an example of. But for our purposes, this is the place to start. Then the Vagabond Group was discovered by Thompson, and that's about in 1971. And it was generalized by Higman. 1974, that's Graham Higman. And the connection among all of these things will be will clear a little bit later. The next example, oh yeah, Smirnov takes this idea of surjective pairing functions and generalizes it to what he called Cantor algebras. And these are very simple theories of a surjective pairing function. Now, my interest starts with Backus's FP because the constructions inside a surjective pairing function are part of the programming language FP. That drew my attention. Then this was generalized into a categorical setting. And one of the things I want to do in this talk is to explain why this categorical setting is particularly useful in proving certain results about the group itself. And Lambeck and Scott did this in developed the notion of a Cartesian monoid, and that's what I will describe it as. These are 2 separate papers in the same volume in 1980. And Fried and Heller rediscovered this idea. Actually, what they discovered was the positive part of F. That is the monoid that generates the smaller of the groups, F, in a very nice paper, which it's 1993. And I rediscovered this in 1996, I guess it is, tops. The total operations of piecewise shift. It sounds better in French, which turned out to be a faithful representation of the free Cartesian monoid of Scott and Lambeck. The notion, again, was rediscovered by Berger in, it says here, 2007, I guess. And he reproved a number of results and got one very interesting new result. And finally, this brought to my attention that Gray and Pardue, in an unpublished, I think it's unpublished, generalized the idea of Cartesian monoids to what they call Cartesian quasi-products, monoids, which turned out to be a really useful idea in some of these applications. Okay. So what are Cartesian monoids? So we start with a surjective pairing function from a set to itself. Okay, so every unit set and every infinite set. By the way, I should mention that since I live in set, I'll tend to formulate these things mostly in terms of sets. Take a surjective pairing function and on a particular set and lift it to the space of functions pointwise. So from that we get 4 axioms, which are there on your screen. And the first 2 axioms simply say that left and right projections of pairs behave properly. The last one, of course, simply says it's surjective. And the third axiom is a distributive law, which simply says that the that pairing was lifted pointwise. Okay, so we have 4 axioms. Oh, and I should add, of course, in addition, that what we're going to have is a monoid under the star operation, and I is the identity of this monoid. If we wanted to talk about pairing functions lifted pointwise that were not surjective, we simply drop the last axiom. Okay, good. Now, these axioms have a free model, and what logicians call a free model, a free object, which we'll call CM. And if we drop the last axiom, we get what Gray and Pardue called quasi-products, and it has a free model, which I'll call CQ. Okay, so what do I want to say about these things? Well, Higman observed that the Vagabond group, the largest one, that's the one I'm interested in. That the Vagabond group, and the others, of course, could be realized as a subgroup of the automorphism group of finite trees. Okay. And what we're going to find out is that by moving from surjective pairing functions to the monoid in the categorical formulation, okay, of course, these things form trees, the free model form trees, and we're looking then at the a subgroup of the automorphism group of these trees, that by passing to the Cartesian monoid itself and looking at the group, so every monoid has a group, looking at the group of CM, that the group of CM is actually isomorphic to the Vagabond group itself. And of course, what it is doing is acting by left multiplication on the monoid. This automatically gives us a faithful representation of the Vagabond group in CM itself. And the objects of CM can be thought of as, well, there are equivalence classes of terms that we get from the language of the monoid here. That nice representation is going to allow us to apply certain techniques. Whoops, I had a better chalk here. Certain techniques that will allow me to settle certain questions. And the kind of question that I'm interested in is the following. Being a logician, we are interested in decision problems. And I'm interested in decision problems of the following sort. Suppose I'm given a finite number of elements of V and another, say F, okay, element of V, can we decide by an algorithm whether or not F is in fact in the subgroup generated by that finite number of elements of V? So that's the kind of decision problem that I want, the membership problem. And what we're going to prove, in fact, is that the membership problem is decidable. That is, it's an algorithm that decides the membership problem. And the algorithm is based on exactly on this representation. So that's why I claim that this is indeed an application of category theory to, in this particular case, group theory. There are other results of the same sort that use this technique, but it's somewhat limited. So I'll try to use the time that I have to explain how this proof works. Whoops, no, that's not what I want. Whoops, that didn't go too well. I'm having trouble getting to the next slide. Nope. We'll get there. Oh yeah, thank you. All right. So first, so what techniques are we going to use? Yeah, so we're going to be, as I said, this depends on the representation of the group, and for that matter, a very large submonoid of this group, of CM. And the techniques we're going to use are expression-based, that is, the rewrite system. So here we have a rewrite system that consists of 7 rewrites. Okay. And these rewrites say the following. The first two simply say that projection is projection. And we have the distributed rewrite. 2 rewrites for the identity because of the way in which, well, this may be familiar from theory of monoids, but the left identity behaves a little bit differently from the right identity, so they need to be separated. Okay. And then for surjectivity, it's convenient for the theory of rewrite rules to have 2 rewrites rather than 1. The first rewrite here being what happens after you distribute X. Okay. So I'll be referring to the first, let us say the first 5 rewrites as the rewrites corresponding to CQ. Quasi-product, that is non-surjectivity. And then the last 3, that 5 gets included in both. We'll give, if I add these together, then I get the full CM. Okay. And what theorems do we want out of this? The theorems are pretty straightforward from the theory of rewrite rules. Okay, every sequence of rewrites eventually terminates in a unique normal form. Okay, Church-Rosser theorem and termination. It's not surprising at all. And indeed, one really useful corollary to this approach is the following, and that is postponement. Okay. And that is that the last 6 and 7 can all be done at the end. And of course, 5 may be used as well. So 5 may be used in the first, in the initial reduction, and it could be used at the end as well. Okay. And so that will give us unique normal forms. And let me emphasize here that the normal forms have a really nice structure, really very pleasant structure, because of the distributive law. So normal forms look like the following. There's a binary tree built up using the pairing operation. Okay. And at each leaf, is a string of L's and R's, lefts and rights, okay, where the empty string is I. Empty string is I. Okay, so this is the shape of normal forms, okay? And indeed, if we look at normal forms with respect to the first 5, that those normal forms can be expanded and contracted. Contraction means applying the rewrite rules by 6, 7, and, well, we don't need 5 there. By 6 and 7 can be expanded and contracted, okay, to give us different shapes. And one nice consequence of that is, I'll just give an example. There's a longer list here. Yeah, so these are the characterizations, but indeed what I'll do is I'll just simply state one of them, the one that we actually need. So what we'll say is that, corollary, F element Cm is a right invertible. That is, we can solve this. If and only if. Okay. So F in normal form. 1 through 5. Oh, no, let's take it 1 through 7. If and only if F can be expanded so that all of the strings have the same length say D, and all are distinct. Okay, that is, if you look at the normal form, what do I mean by expansion here? It's easier to draw these pictures. So what I could do, for example, is I could take this and copy it twice, put an L there and an R there. And that's an expansion by 6, reduction rule 6. Okay, now then, when you multiply 2 of these, oh, I forgot, yes, let me add 2 interesting submonoids, okay? They can't be, yeah, I should add, one of the things that I proved in the last century was that CM is simple. There's no non-trivial homomorphisms, and that's stated in an earlier slide. And so you really can't expect that proper submonoids will actually be Cartesian monoids themselves. So I'll be referring, when I refer to submonoids, I mean strictly submonoids, not Cartesian monoids. So the right invertible ones and the left invertible ones are indeed submonoids of this. And
Richard, you're getting into, hi Richard, you're getting into your question time, okay?
sorry?
You're starting on your question time right now, kind of.
Yeah, okay. Yes, let me get
Okay.
to the, yes, no time, running out of time. Well, I stated the main result. Yeah. So let me say this. This talk was not designed for 20 minutes. It should have been though. So we'll skip that. We'll skip that. Yeah, let me emphasize the model. Okay, by looking at the way in which normal forms multiply, okay, it's very natural to look then at a model for such multiplication in the following way. It's modeled by, well, let's just take the initial multiplication to be a string, okay? And then it's going to be multiplied by normal forms. So it really looks like the operation of a stack, okay? And where the input alphabet is the set of normal forms, and the stack, the initial stack, is of course just a string. Well, let's put it this way. The model itself is the model of GGH, Ginsburg, Greibach, and Harrison. Well, let me just emphasize the following, that again, you're led to this model by looking at the normal forms in the Cartesian monoid, okay? And the model allows us to prove that the problem is that I mentioned before is decidable. Okay, so rather than trying to fit the rest in, I'll stop there and ask for any questions.
Thank you very much. We have time for a few, two questions, I think. And I don't see anything yet on the chat. So I am a little bit confused. I don't know if it's the sound issue or something, but I'm a bit confused because I thought that that the equation 5, I thought it was exactly eta somehow, was corresponding to surjectivity of the unique map into the product. I think I must have got it wrong because
Yeah.
can you kind of...
Equation 5 corresponds to surjectivity. Yes.
And surjectivity...
Sorry, equation 4. It's the equation 4. There's only 4 equations. No, it's 5 equations. I keep identifying the 2 for the identity, but yes. Left projection, right projection, the 2 for identity, and then there is the distributive law.
Right.
And that I equals pair LR, that's surjectivity. That says that everything is a pair of its left and right projection.
Right. But I thought that corresponded to eta if we're thinking of that as lambda calculus.
It behaves somewhat like eta, but it's not eta. I mean, yeah, it behaves something. Yeah. Well, you have similar results as you point out. Postponement, for example, like eta postponement. It behaves that way syntactically.
And you know, the problem I was going to say is that if it is kind of what we normally think about as eta, then the question is, normally people in functional programming don't like eta very much, right? So you know that we end up having to decide which etas kind of one is going to pay attention to. So I was thinking whether that conversation about etas can be moved down to the Cartesian monoids, and if the Cartesian monoids have guidelines on different kinds of eta for us or not.
Well, I'm not sure. Yeah. Well, look, the theory CQ without. Yeah. Let me add this that. The CQ is pretty trivial with respect to its monoid structure. I mean, there just isn't anybody who's invertible. So CQ was a technical device, very useful because of. But I mean, everything I said about the Thompson group does not apply to CQ.
I think I'm still kind of a little bit lost, but I probably have to read the paper properly. Do we have other questions, people? I don't see kind of questions at the moment. Maybe there is one, sorry. Yeah, Phil has a question. The question is there an analog of ether expansion? Phil, do you want to talk? I don't.
Yes, I can talk. Okay, Rick, I was just wondering if there's any, this is Phil Scott. I just wondered if there was any notion in your rewriting of looking actually at eta expansions in context, of course, and being able to do rewriting that way, which would give you sort of analog, I mean, give you the Cartesian analog of long beta eta normal forms, of course.
Yeah. That's what I was.
Formally speaking, there's, yeah, let's put it this way. That's a very interesting question syntactically, if there's a general theory of eta expansions that would cover this case as well as eta expansion in the lambda calculus. Now, of course, you get a similar, the pointwise expansion would apply to type lambda calculus with pairing. So there's a similarity. However, there's a similarity between extensionality and surjectivity, yeah.
Okay.
And it might be interesting to put that in the categorical context. The reason why yeah, let me emphasize, I haven't thought about this issue for the following reason. The reason was that CQ, the theory without surjectivity, was for me a tool to get the nice correspondence to the push-down stack automata of Ginsburg, Grayback, and Harrison. But as I said, the group that I was interested in, the Vagabond Group and its related structures, okay, they don't exist inside of CQ because the group of CQ is triggered. Now, of course, the automorphism group is still there, but it's not represented as the group of the monoid. So, that's not a good answer.
I see. Thank you. Thank you.
Now, I think we should finish the session kind of the moment, but of course there is more questions that can be discussed in the Zulip channel afterwards. So I want to thank first the speaker again. Thank you very much. We will continue the conversation, but yeah, I think all good things come to an end. And this was the last session of the ACT conference 2020. And I think we had a great time. Lots of us kind of enjoyed ourselves very much. So I think we should kind of give a hand of applause to our organizers and all the people who kind of been putting so much effort into making this conference work, despite COVID-19, despite the distance, despite the Zoom problems and other stuff. So thank you very much to David, Brendan, Dave, Bob, kind of John, and lots of people. You know, I shouldn't even started this list because I'm going to forget very important people. I know that, and I apologize in advance, but thanks a lot for a beautiful conference. And I hope everyone is going to join on the clapping for the organizers. Thank you, guys. Now, I think David wants to have a final word.
Just thanks, Valeria, and thanks to everyone for the great conference. I had fun. I think I learned a lot, and I know a lot better what an online conference is like compared to an in-person conference. And so again, I just want to thank all the organizers, David and Paolo and Brendan and Destiny, and also Protocol Labs. They sponsored inclusivity. They were a gold sponsor of inclusivity. And so they helped students get tablets, and they're helping next year also. Like, we have funding for next year also from their generous donations. So thanks to them. And yeah, thanks for everyone for coming, and see you next year in Cambridge, England. Thanks everyone. Great conference.